So far, we have a mathematical model for flow with friction known as the Fano flow, and we've understood from it what is the influence of friction on the flow Mach number as well as other flow variables. In this example video, we'll look at how to use that mathematical model in a more useful, tangible form. That is, if we are given some inlet conditions, can we find out what will be the exit condition of a flow with friction acting on it? So let's consider a flow through a pipe of diameter 0.4 meters with a length 0.5 meters. We are told the inlet Mach number is 3.5 and the friction coefficient is 2 times 10 to the minus 3. We are asked to calculate the exit Mach number and the further length required downstream to choke the flow. We are also asked to compute the ratio of the exit stagnation pressure to inlet stagnation pressure, while assuming this ratio of specific heats gamma is 1.4. We'll begin by first computing 4F L star over D at the inlet location, which we'll designate as location 1 over here. Now we can compute this value using an expression that involves Mach numbers as we have seen earlier in our theoretical development. But instead of doing the numbers by hand, we're going to use this excellent compressible flow calculator developed by Professor Davenport from the Department of Aerospace and Ocean Engineering at Virginia Tech. So let's go to the flow calculator, which I'm sure you've seen in earlier sections of the course such as isentropic flow and shock waves. Alright, since we are interested in Fano flow, I'm going to go straight down into that part of the calculator. We were told that the inlet Mach number is 3.5, so let's put that in. We've been asked to assume gamma is 1.4, and that is the default value. We'll leave it as it is. If I hit calculate, I can get a value for 4F L star over D as 0.586. Similarly, I can also compute P0 over P0 star using this calculator to be this value. I'm going to store both of these numbers for further use. So let's go back to the problem. Let's fill in those numbers. We can now know that 4F L1 star over D is this value, and P0 in over P0 star is that value. Alright, now we know that the difference in 4F L star over D at the inlet to that at the exit should be equal to 4F L over D, where L is the length of the pipe. Knowing this, we can rearrange this expression as 4F L2 star over D equals 4F L1 star over D minus 4F L over D, where 2 is the exit location. Now we have a value for 4F L1 star over D using this flow calculator, and we can compute 4F L over D because we're given all the parameters we need to compute that, such as friction coefficient F, length, and D. So let's do that, and that comes out to be 0.576. Let me just make sure that I got this number right by using the flow calculator, in which there is a scratch pad. So let me take that value, minus 4 times F, which was given to be 0.002 or 2 times 10 to the minus 3, times the diameter, which was 0.4 meters, divided by the length 0.5 meters. If I hit calculate on this, I get 0.58, and let's see if that's the number I had from my earlier computation. Oops, I think I made a mistake. It needs to be 4F L over D, so this is 0.5 divided by 0.4. Alright, so that is 0.576. Now let's go back to the main screen, and yes, we have 0.576 4F L over D. Alright, once we have 4F L2 star over D, we've been asked to calculate the further length required downstream to choke the flow, that is L2 star. We can rearrange this expression to calculate L2 star to be 28.82 meters. That is, if we continued this pipe for another 29 meters almost, that's when we'll reach choking conditions with this amount of friction acting on the flow. So we have a long distance to go before the flow will choke. Therefore, that's good news. We're not in any danger of choking flow in our, if this was our combustor, we're not going to choke the flow because of friction. Alright, the next step is we are going to calculate what is the exit Mach number. To do that, again, I'm going to go back to the flow calculator. I have a value for 4FL2 star over D as 0.576, or in fact it was a much longer number. I just abbreviated to truncated to 0.576. Let's go back there. The actual value was 0.576 with a few more decimal points. Let me use that again in the Fano flow calculation part, put that in, but from the drop down menu I am going to be using 4FL over D supersonic. Now notice that there are two options, subsonic and supersonic. Because we started with supersonic flow with Mach number 3.5, and we know from our theory that at worst the lowest Mach number you can reach is Mach 1 because of friction. You can never go subsonic, therefore we have to choose the option supersonic. And if I say calculate now we get a new Mach number. This is going to be the exit Mach number, and that's what we are asked to calculate. We also have P naught over P naught star at the exit. So we'll take these two values, store it in our problem evaluation, and let's do that in the next step. Now we got this Mach number using the calculator, but I just want to remind you that behind the scenes, when we supplied the value 4FL2 star over D to be this number, the calculator is using this Fano flow expression and trying to compute what value of Mach number, and we have told it it's supersonic, will satisfy this equation given that the left hand side is this number. And that's how we get this M exit to be 3.41. Alright, so the next step, we are asked to calculate the ratio P naught exit to P naught in, which can be written as P naught exit by P naught in equals P naught exit over P naught star divided by P naught in divided by P naught star. And again, we have values for P naught exit over P naught star that we have been storing along the way, which is 6.245 here, and P naught in over P naught star was computed at the very first step using the flow calculator as 6.789. Substituting that and evaluating it gives us 0.92. That is, we incur roughly 8% pressure drop as the flow goes through this pipe with friction acting on it. I hope that was a useful example problem for you to look at in order to see how to apply the equations that we've developed for Fano flow.